degree protractor, and you can get the bearing. The bearing is a 3-figure number. You might have to do, if this is a displacement, they might ask you for a velocity. Well, displacement is velocity times time. Distance equals speed times time. So if the question's asking you for speed, then you do speed is distance over time. If the question's asking you for velocity, then you say velocity is displacement over time. Electricity. We are getting there. Hang in there. We've got electricity to do and we've got energy to do, and then we are sorted. Fantastic. Brilliant. Doing well. There you go. There's your motivational chat. So what the hell is electricity? Electricity is what everyday people call electric current. What is electric current? Electric current is when particles, in our case electrons, move electric charge. And in our case these are electrons, and electrons carry negative electric charge. And when electrons carrying negative electric charge move through something, in other words, the electricity goes through something, there is always a heating effect and there's some magnetism. Now the heating effect comes from these particles, these electrons, forcing their way through something, and there's friction. So this is stuff like how light bulbs work, because that little filament gets so hot it gives out light. Well, this is how filament light bulbs work. LEDs are a bit different. But this is the use of the heat from electrons, and obviously things like electric heaters, they make use of the heat from the friction of the electrons too. Something we don't often think about though is that this moving electric charge, this is what creates magnetism. Now, who cares about that? Well, this is how electric motors work. So think about what electric motors are in. Well, they're in all sorts, from your mobile phone to the pumps which work your electric shower, to all these consumer gadgets in your kitchen. So whenever you've got electrons moving, there's heat, which is from the friction from the electrons themselves, and you've also got magnetism, and that's from the electric charge, which the electrons happen to carry. Yes, okay, so this is the use of it. The electrons themselves, the friction making heat, so bulbs, cookers, central heating systems. Yeah, think about the poor people in Ukraine. They don't, when electricity is stopped because the Russians have blown up the power stations, one of the main things they're suffering with is they're not getting any heating at home because they don't have electricity, which is really bad, really tragic. And let's hope it's all over soon. When electric charge moves, then you have magnetism, and this is how all electric motors work, for example, in your phone and your household appliances. So the quantity of charge, Q, being delivered to a point, is the current, the electric current, multiplied by the time. So the quantity of charge being delivered to a point is the current multiplied by time. Charge measured in coulombs, current measured in amps, time measured in seconds. So current is the rate that charge arrives at. It's a bit like charge like the quantity of water. The current is like the flow rate of a river. So if you've got like a massive bucket you're wanting to fill up with, or massive container you're wanting to fill up with water by putting it in a river, the amount of water in your bucket is the current of the river times by the time. Maybe it helps, maybe it doesn't. That formula, quantity of charge is current times time, here's the triangle, Q equals IT. Q, quantity of charge, current is I, and time is little t. So here's our picture of an atom. An atom has a nucleus in the middle. The nucleus is made of neutrons and protons. Protons have positive electric charge, and the electrons around the outside have negative electric charge. Opposite electric charges attract. So this is why the electrons like to stay associated with their nucleus, and electrons staying associated with the nucleus is what an atom is. So if you want these electrons to be pushed away to move down a wire, like in that picture, then there's got to be some sort of electrical pressure to push away those electrons, and that electrical pressure is called a voltage. A voltage, electrical pressure, is actually an electric force field. So anything with electric charge has its own little electric force field. So here are the electric force fields around the electrons, but if you have a much bigger overall external electric force field, which I've done in black, then the individual electric force fields of the electrons respond to that, can get pulled along by that, and so, for example, a 1.5 volt battery gives each chunk of charge 1.5 joules of movement energy. So the overall electric force field drags along the particles, which are the electrons, which are at the middle of those individual electric force fields. What's electrical power? Electrical power is the rate that energy is used up by an electric device. So something like an electric drill needs a lot more energy per second arriving at it than a little filament bulb. So if you've got a very powerful device which uses up a lot of electrical energy per second, it's more powerful. It can do stuff. If you've got an electrical device which is needing to output a lot of force, a lot of torque or whatever, then it's going to need to be a powerful device. It's going to need to use up a lot of energy, electrical energy, every second. It's going to be more expensive to run, but maybe it needs to be more expensive to run because it needs more energy every second. If you are outputting more energy per second, then you need more energy per second of input of electrical energy coming in to begin with. So power is energy divided by time. Energy is in joules, time is in seconds, power is in watts. So here's the formula: P equals E over T. There are three other power formulas: P equals IV, P equals I squared R, and P equals V squared over R. These are the triangles. Okay, how do you know which triangle to use? Do your shopping list. Series and parallel circuits. What is a circuit? A circuit is a circle. So there has to be a complete circuit for electricity to move around something. If there's a break in the circuit, electricity isn't going to move around it, and this is how switches work. Okay, circuit diagram, real life diagram. Series, there's just one loop. So this is the picture, battery, bulbs, and here's the circuit diagram. They're all in one loop. Yes, I know you've got multiple different leads, but there's just one loop. Parallel circuits, there's more than one loop. The loops are separate loops, they just happen to share the same voltage source. So here you have a Hoover plugged into the mains, and here you have some hair straighteners plugged into the mains. So there's the circuit symbol for the mains, and here's the circuit symbol for a heater in the hair straighteners, and here's the circuit symbol for a motor in the Hoover. And I've tried to show with the different colours. You've got your blue loop, which is the heating loop, and then you've got the red loop, which is the electric motor loop. And if one of these circuits stops working, then the other stays working. This is why everything at home is plugged in parallel. So parallel is separate loops which just happens to share the same voltage source. So if you've got a series circuit, as you add more and more components in series, so if you were to add a third bulb and a fourth bulb and a fifth bulb, the current would go down, but the current is the same in all parts of the circuit. So the current measured there would be the same as the current measured there, as the same measured wherever. But if you add more and more bulbs in, the bulbs would get dimmer and dimmer and dimmer because the current goes down. And we did that in S2. In parallel circuits, the total current associated with those plugs is going to be the current through each of the individual circuits added together. So in this case, if you wanted the total current there, A, it would be the current through this loop, which is A1, plus the current through that loop, which is A2. If you plug in, if you've got a socket like this and you plug in some high current devices, like an electric heater and some hair straighteners, then you can end up causing an electrical burn to the socket, because if that current is high and that current's high, then the total current is going to be really high, and that burns the socket, which is not good. So current in series is the same in all parts of the circuit, and it gets less and less and less when you add more stuff, but current in parallel loops adds up. People find it hard to understand and remember what happens in parallel circuits with the voltage. So here's an analogy, maybe it works, maybe it doesn't. So here is a water tower. You've maybe seen the water tower at Condor, great big concrete structure. I want you to imagine a water tower with a bunch of water pipes coming off it. And these water towers are huge, by the way, so that's, well, not to scale, but it gives you an idea of scale. So here are some water pipes coming off the water tower. Now, the water pressure in each of these pipes is the same, and it's equal to the water pressure from this tank. Okay, so in parallel circuits, because they are independent circuits, independent loops attached to the same voltage source, then the voltage in each of the parallel loops is the same, and it's equivalent to the voltage of the supply voltage. So here we have, well, the same circuit as before. The voltage push from the water tank is whatever, and each of the loops attached to the water tank gets the same voltage supply, same voltage source as the whatever that voltage source there is. So in the mains it's 230. So if the voltage supply here is 230 volts, then this circuit gets 230 volts and this circuit gets 230 volts. It's like the circuits are like these little pipes coming down, and the pipes all get the same voltage, which is supply voltage. So V in each loop will be 230 volts push, and the supply voltage is like the voltage pressure or the water pressure in the water tower. With series circuits, the voltage push is shared out, and it has to be because there's only one pipe. So if there's only one pipe, then the push down the pipe has to be shared out. So if, I don't know if you can see, if the total push down the pipe is 24 volts from this battery in this case, then you know that the share which each of these components gets has to add up to 24. So 6 volts plus 2 volts plus 16 volts, that's going to equal 24. And the bigger the resistance, the bigger the share of the push down the pipe needed to get that current through. Resistance as a quantity is measured in ohms. If you've got a component, if you're designing a circuit, then you do need to know what the total resistance is. So if you're an electrician, you'll do this sort of calculation all the time. If components are in series, it's dead easy. The total resistance is the resistance of that plus the resistance of that plus the resistance of that. In parallel, the total resistance is trickier to work out because you've got to use this 1 over formula. So 1 over RT equals 1 over R1 plus 1 over R2 plus 1 over R3. The most commonly used electrical formula is V equals IR. Voltage is current times resistance. There's the triangle. Voltage in volts is current in amps times resistance in ohms. So here might be a question for you. So we've got a battery, we've got a bulb, there's the ammeter in series to measure current, and you've got the voltage push across the bulb, and the question is saying what's the resistance of the bulb. So you've got I, you've got V, and you can solve to find R. R equals V over I. So this is kind of, I suppose, a bit of a historical hang-up, which, you know, as a electrician you won't really think too hard about this, but it's still on the SQA syllabus. Where the hell did this formula V equals IR come from? Well, if you've got a component and you measure the voltage of, you put it in a circuit and you give it some voltage, voltage pushes current around the circuit and it lights up, and then you can increase the voltage, write down the new voltage, write down the new current. Increase the voltage a bit more, write down the new current. Increase the voltage a bit more, write down the new current. You can plot voltage and current points, and as you increase the voltage, the current goes up. You kind of know that because voltage pushes current around the circuit, but if the current goes up in step with the voltage, then you get a straight line. Now there are some components, however, which don't allow the current to go up in step with the voltage. So components which do allow the current to go up in step with increasing voltage give a straight line, for example resistors, and it's said that these components follow Ohm's law, but components which do not allow the current to go up in step with increasing voltage give a curve, for example a bulb, and these do not follow Ohm's law. If you get a graph like that, then you can also read off voltage and current readings from the graph and do R equals V over I. Alright, this formula V equals IR comes from components which follow Ohm's law come from the straight line, but you don't really need to know too much about that. What you do need to be able to do is read off V and I values from a VI graph to calculate R, and if it's a straight line, well, that follows Ohm's law, but don't worry too much about that. Automatic response circuits. I suppose these are sort of like the vector arrows of electricity, and that people find them tricky. Why the hell do we want to know about automatic